Good morning, student. I am Dr. Gnanasekar, Associate Professor, Department for Medical Electronics, Savita Engineering College. Today we are going to discuss about physiology of acid-base balance. So this topic is in the 4th unit of Medical Instrumentation, MD8401. Introduction. So acid-base hematosis is the part of human hematosis concerning the proper balance between acids and base, in other words the pH. The chemical and the physiologic process responsible for the maintenance of the acidity of our body fluids. Acid-base hematosis, chemical process, extracellular and intercellular buffers. The physiologic process, the excretion of volatile acids by the lungs and fixed acids by the kidneys. Acids. Acid can be defined as a proton, H+, which is a donor, hydrogen containing substance which dissociate in solution to release hydrogen ion. So you can see the image where H+ and OH- is being distributed. Whereas the acids, physiological important acid includes carbonic acid, phosphoric acid, pyruvic acid and lactic acid. And bases. Bases can be defined as a proton H+ acceptor. Previously, acid is a donor, whereas bases are acceptor. Molecules capable of accepting a hydrogen ion OH-. So you can see the OH-, which is in blue color. And bases, mainly these are the physiologically important bases, include bicarbonate and biphosphate. pH scale. So what is pH? Which refers to the potential hydrogen, the expresses of hydrogen ion concentration in water solutions. Water ionized to a limited extent to form equal amount of H+ ion and OH- ion. So H2O is equal to, which is a reversible reaction. So hydrogen positive ion plus OH- ion. So here you can see H+, which is nothing but an acid ion, and OH- is a base ion. So pH scale. So for water, the neutral part where it have a pH of 7. If it's acid, where the pH will be less than 7, and if the pH is greater than 7, it is a basic. So our normal blood pH is about 7.35 to 7.45, and the pH scale where we can see the ECF, that is extracellular fluid, of 7.4. So here you can see the acidosis, normal condition, and alkalosis. So acidosis is nothing but the normal value below, that is pH of ECF 7.4, below will be acidosis, and for alkaline it will be above 7.5, so 8. Even if the level gets down to 6.8, death is assured, and if it increases to 8, death assured. So the determination of acid-base status. So now the balance between the acid-base is being given as an example for a pH. So pK is nothing but potassium plus log HCO3 by CO2. So this is because of Anderson-Hasselbalch equation. Normal acid-base ratio is 1:20. So for a pH of arterial blood, that is indirect method. For acidosis and alkalosis, what is acidosis? A condition in which the blood has too much acid, frequently resulting in decrease in pH of blood. Alkalosis, a condition in which the blood has too much base, that is occasionally resulting in increasing in blood pH. So what actually happens? So if it is acidosis, a hydrogen ion increases higher and OH negative ion decreases. Whereas for alkalosis, hydrogen ion will be decreasing and OH will be increasing. So pH changes have dramatic effect on normal cell functions. So these are the changes when alkalosis or acidosis happens. Changes in excitability of nerve and muscle cells, influences enzyme activity, influences potassium level in the neurons. So change in cell excitability. So pH decreases, more acidic, depresses the central nervous system, can lead to loss of consciousness. And pH increase may cause over excitability, tingling sensation, nervousness, muscle twisting. So influence of enzyme activity. So you can see the pH increase or decrease, what happens is it alters the enzyme, rendering it non-functional. That means you can see the shape where the enzyme molecule with the substrates which change the different shape. So due to this, the shape can be altered. Influence of potassium level. When reabsorbing there is Na plus from the filtrate of the renal tubule, so a potassium or a hydrogen is secreted or exchanged. Normally Ka plus is secreted in much greater amount than hydrogen. So influence of K level. So if the concentration of hydrogen are high, that is acidosis, then H plus is secreted in a greater amount. This levels leaves less potassium than usual excreted. The resultant K retention can affect the cardiac function and other functions. Source of hydrogen ion. So CO2 plus O2, there is a water, that is equal to H2CO3, and where it won't be the same, so hydrogen ion and HCO3 will be formed. Regulation of acid balance. So two types of acids are produced in the body. So the volatile acid, CO2, produced during the metabolism of carbohydrates and lipids. The non-volatile acid, metabolism of protein, example sulfuric acids. So the compensatory mechanism. So chemical buffers, respiratory regulation and renal regulation. For chemical buffers reacts very rapidly, less than a second. Respiratory regulation reacts rapidly, seconds in minutes. Renal reacts slowly, minutes to hours. Intercellular shift of ion. So the acid-base buffers maintains the pH by binding with free hydrogen ion, combination of weak acid and a base. Three major chemical buffer systems: bicarbonate system, phosphate system and protein system. So if a bicarbonate buffer system happens, so what are the carbonic acid which affects the respiratory system, and bicarbonate for a renal system. And H2CO3, that is which will be separated into H plus and HCO3 plus. Hydrogen ion generator by metabolism by ingestion react with bicarbonate base to form more carbonic acid. And bicarbonate buffer solution equilibrium shifts towards the formation of acid. So that is which when hydrogen loses, then there is vomiting, causing carbonic acid to dissociate, yielding replacement of hydrogen and bicarbonate. So bicarbonate buffer system, which is nothing but the same. CO2 plus O2 H2O will give H2CO3, that is hydrogen ion and carbonic acid, where the addition of lactic acid will lead to exercise, and loss of HCl will give about vomiting. And for phosphate buffer system, most important in the intercellular system, where the hydrogen ion will be reduced. And phosphate buffer, where the cell has the regulation with the urine, concentration of the intercellular within the kidney tubule, more phosphate ion are found in tubular fluids, more powerful than bicarbonate buffer system. Protein buffer system, the protein excellent buffer contains acid and base group that can take up hydrogen plus. Protein explicitly is extremely abundant in the cell, so more limited number of protein in the plasma reinforce the bicarbonate system, the ECF. Hemoglobin buffer, hydrogen form from metabolically produced CO2 in the plasma only. As hemoglobin releases CO2, it gains a greater affinity to H plus. And the reverse, to have OH. And for respiratory system, where it depends for the brain control, so the pons, the respiratory center and the medulla oblongata. And chemosensitive area, where it will be giving a effect by stimulating the respiratory system. And this is the respiratory control for pH. Cell production of CO2 increases. CO2 plus water reacts to form H2CO3. H2CO3 will be separated by H plus and HCO3. That is, if H increases, it is called acidosis, and pH drops. And H plus stimulates a respiratory center in medulla oblongata. Rate and depth of breathing increases. CO2 elimination in lungs. pH rises towards the normal. Renal response, when the kidney compensates for acid-base imbalance within 24 hours and responsible for long-term control, the kidney is response. To acidosis, retains bicarbonate ion and eliminates hydrogen ion. To alkalosis, eliminates bicarbonate ion and retains hydrogen ion. And electrolytic shift, where you can see the compensatory response will be with the buffer solution like hyperkalemia, diabetic ketoacidosis, and for alkalosis, it is tendency to correct alkalosis by hypokalemia. So that is hydrogen and potassium shift. Thank you.